Welcome back to the Explainer. If you've ever just sat there, jaw on the floor, looking at the stunning visuals in a modern video game, or maybe you've been messing around with AI image generators, well, you've been witnessing the sheer power of a graphics card. So today, we're going to pull back the curtain and see exactly what makes these things tick. So let's just start with a big question. Just how powerful are these things really? I mean, when you're deep in a game, what is actually happening inside your machine to make all that magic happen on screen? Okay, get ready for this number. To run a visually dense game, something like Cyberpunk 2077 with all the settings cranked up, a high-end GPU is performing about 36 trillion calculations. And that's not over the course of a minute. That is every single second. 36 trillion. To even try and wrap our heads around that, think about this. Imagine every single person on Earth, all 8 billion of us, doing one math problem every second. Well, to keep up with what that one graphics card is doing, you would need the entire population of 4,400 Earths. It is just a mind-bending, almost unimaginable amount of computing power. Okay, so how on earth is that even possible? What makes a GPU so radically different from your computer's main brain, the CPU? Well, it all comes down to two completely different philosophies for getting work done. And this is probably the best analogy you'll ever hear for it. Your CPU, it's like a jumbo jet. It's incredibly fast, super flexible, and it's designed to handle a few very complex tasks with almost zero delay. That's what we call low latency. A GPU, on the other hand, is a colossal cargo ship. It's not nearly as fast for any one single package, right? But it is built to move an unbelievable volume of simple, identical containers all at once. That's high throughput. Two different jobs, two totally different tools. All right, so let's pop the hood on this cargo ship and see how it's actually built. What's the physical anatomy of a GPU that lets it handle this insane workload? We're going to zoom all the way in. Okay, so level 1. At the very center of everything is the GPU chip itself, the die. It's this tiny sliver of silicon, something like the GA102 chip you see here. And you have to imagine it like a sprawling city, just jam-packed with billions and billions of microscopic transistors. This is the command center for the whole operation. But this city, it isn't just one giant chaotic block. No, it's neatly organized into a few big sections. These are called graphics processing clusters, or GPCs for short. So if the chip is the city, these GPCs are like the main districts or boroughs. Okay, let's zoom in again, a level deeper. Inside each one of those GPC districts, we find dozens of what are called streaming multiprocessors, or SMs. Sticking with our city analogy, these are like the individual neighborhoods within each district. Each one is a pretty powerful little unit all on its own. And finally, we get to the street level. Inside every single SM are the actual workers. These are the thousands upon thousands of tiny, highly specialized cores. You've probably heard the names: CUDA cores, tensor cores, RT cores. Each one is basically a tiny, simple calculator, just waiting for an order to do one small piece of a much, much bigger job. But here's where things get really, really interesting from a manufacturing standpoint. When you're making something this complex, with billions of parts on a microscopic scale, perfection is basically impossible. You're always going to have tiny defects. So what do companies do? Throw away an entire chip because a few cores are faulty? No way. They use an incredibly clever process called chip binning. Just look at this. This is fascinating. The 3090 Ti, the 3090, the 3080 Ti, and the 3080, they are all built on the exact same physical GA102 chip. The top-of-the-line 3090 Ti is what you'd call a perfect chip, where all 10,752 cores work flawlessly. But the 3090? That's the same piece of silicon, just with a small handful of defective cores disabled. The 3080 Ti has a few more turned off, and so on down the line. It's a brilliant way to take one production line and create a whole stack of different products, all based on how close to perfect each individual chip comes out. So, okay, we've established we have this massive army of thousands of simple little workers. But how do you actually command them? How do you get this huge, sprawling workforce to do something useful all at once? Well, this is where the real secret sauce of the GPU comes in: parallel processing. The key is that GPUs are designed to tackle a very specific type of problem. It's a problem that computer scientists call, and I love this is the real technical term, embarrassingly parallel. And it's a great name because it means exactly what it sounds like. A huge problem that is just laughably easy to break down into thousands or even millions of little independent tasks that don't rely on each other. And the strategy they use to do this is called SIMT. That stands for Single Instruction, Multiple Threads. Just picture a general shouting one single order to an entire army. Or, going back to our cargo ship, a foreman giving one simple instruction for every single container. It's one command, blasted out and executed by thousands of workers at the exact same moment, but each one is working on its own little piece of data. Let's make this super concrete. Imagine we have this 3D model of a cowboy hat. It's made up of 14,000 individual points, or vertices. Now we need to move that hat into the actual game world. A CPU might do this one point at a time, which would be slow, but a GPU, it creates one single simple math instruction. Hey, add the world's position to your current position. Then it broadcasts that exact same instruction to thousands of its cores simultaneously. Each core grabs a vertex, does that one simple bit of math, and bam. In an instant, all 14,000 points move at once, and the entire hat snaps perfectly into place. That is the raw power of parallel processing. And this is where the story gets really wild. Because this whole incredible architecture, this massive parallel processing engine, it was originally designed for just one purpose: to make video games look prettier. But as it turns out, having a machine that's really, really good at doing one simple thing millions of times at once is useful for a whole lot more than just gaming. I mean, of course, it's still the heart and soul of modern gaming, but then people realized it was perfect for cryptocurrency mining. Why? Because mining is basically guessing a winning lottery number over and over again, an embarrassingly parallel task. And now, in what might be the biggest shift of all, GPUs have become the undisputed engine of the AI revolution. Training those massive neural networks requires trillions of the exact kind of simple calculations that GPUs were born to do. So it really all comes full circle, doesn't it? A piece of technology that was born purely out of the desire for more realistic graphics in video games has, almost by accident, become the fundamental key to unlocking artificial intelligence. And that really leaves us with a final massive question. If this power was designed for graphics and then repurposed for crypto and AI, what new, world-changing problems are just sitting out there, waiting to be solved by this incredible power of parallel processing?